All right, this was the second 2.4 assignment, 9 through 16. Um, Basically using the formula for a tangent slope to find some tangent slopes. That was the idea. So number 9, 10, this is pretty much exactly the work that you would have seen within your course pack. Um, Having the work and being able to follow it, two very different things. I would hope that everybody could follow the work in parts B and C, because that's just taking a slope and a point and writing the equation of a line. So that's just algebra 1 stuff. We did need to realize that normal lines were perpendicular um, to tangent lines, and so we have to use opposite reciprocals. The opposite reciprocal of -4 is positive 1/4. The opposite reciprocal of -2 is positive 1/2, and so on. The real work, though, is this stuff. And so just to make sure that you see as much of this as you need to, I'm going to go through 9, 10, 11, 12 really quickly. Probably 11 will be the most requested problem because it was the only non-polynomial relationship. Um, and I will work those out. I'm not going to go through the parts B, C, because I think you can handle that aspect of it. But let's find some tangent slopes. All right. So number 9 is all about the tangent slope of x squared at x equals -2. By the way, I'm pretty sure you would all agree with me that a parabola right through the origin at, for its vertex is always going to have negative tangent slopes as we come down, and then those tangent slopes are going to start moving up as it starts to increase. So when they're asking me for -2, I can expect a negative tangent slope. Let's see if we are right in that guess. Here we go. The limit as h goes to 0 of f of -2 plus h minus f of -2 divided by h. Now notice that I'm going to need to find a little bit of information here. I'm going to need to find f of -2 plus h. If you do this within the formula, that's fine, because I think that's how a lot of the work is shown through the course back, but otherwise you could do it off to the side and then substitute it in. So -2 plus h quantity squared is 4 minus 4h plus h squared. And f of -2 is -2 squared, or 4. So what are we going to have here? We're going to have some 4's that cancel. I'm going to be able to factor out an h. And that's always the goal with these polynomial problems, is to get that h to cancel so that I can evaluate this as -4 plus 0 or -4. Remember, we thought there should be a negative slope up here. And sure enough, there was. Now, once I have that slope of -4, I can take the point -2. Remember, they gave me the x value, and we actually found the y value here. I can take the point and the slope and write the equation of the line, and then do the same thing again with the opposite reciprocal slope. And that's it. -4 1/4. Everybody is vastly happy, right? So that's the exact same work I just showed right in here, except they kind of did the algebra within the problem. I did it off to the side and substituted in. Other than that, no changes. By the way, look at the parabola. Look at that slope that we found, -4. They found the intercept was -4. Look at that perfect tangent relationship at that point. And then when we took the normal line, which we found to be 1/4 x plus 4.5 or 9/2. Look at that perfect perpendicular relationship through that point of tangency. Very cool stuff if you follow the rules, right? Let's do number 10, which was very similar, but with just an extra term in the polynomial. We're going to do this guy this time at x equals 1. I, if you guys think about this stuff before you jump in, that would make me so happy, because that's what this whole course is supposed to be about, right? Analyzing mathematics. If I factor that and I get x minus 4, my zeros are 0 and 4, and so it's positive x squared. So what that means is this dude is going to kind of go like this. The vertex is pretty easy because of the symmetry of parabolas. The vertex is going to have to be at 2 something, right? I guess I can plug the 2 in and get 4 minus 8, so negative 4. That's where my vertex is going to be. That's what this problem is going to look like. And at x equals 1, which will be right here, notice that's on the downward, the decreasing part of the parabola, so I should get another negative tangent slope. But you don't have to do that to do this problem. It's just, I love it when you think through it a little bit. So the limit of h goes to 0. I'll do the work within the problem this time. So we're going to do x 1 plus x 1 plus h squared minus 4 times 1 plus h. So that is f of 1 plus h, but now I have to subtract f of 1, and that would be 1 squared minus 4 times 1. So I kind of think it's neater if you label this stuff off to the side, like f of 1 plus h, and then I can just find it, and then I can plug it in, and then I can do f of 1, and I can find it, 1 squared minus 4 times 1, 1 minus 4 equals negative 3, and then I can plug it in. But there's nothing wrong with doing it this way as long as you show all your steps. I used to do it this way. I thought it was faster. Now I'm not so sure. I think it's really personal preference. I just think it's more organized to show your work off to the side and make substitutions. It makes things just a little bit neater, but either way is fine. So 1 plus 2h, right? Make sure you FOIL, and then make sure you distribute. Negative 4 minus 4h. If you forget that negative 4 times h is negative 4h, you will miss the problem. And then this is, remember we said that this was negative 3, 1 minus 4, but when I subtract the negative, I'm going to get a plus 3. Okay? Now, that's kind of a big deal, because we need everything that does not have an h term to cancel out. And this 1 and this negative 4 would not cancel with a negative 3, but it would cancel with a positive 3, right? So I basically have 1 and 3 is positive 4 plus the negative 4. It's gone. I have 2 h's minus 4 h's, so negative 2h plus h squared. I can now factor out the h. Whenever you're ready to factor out the h, you're almost done with the problem. My h's tend to look like it ends a little bit. Sorry. So the limit is h goes to 0 of negative 2 plus h is equal to negative 2 plus 0. Make sure you show your substitution step is equal to negative 2. We thought it would be a negative slope right there, and sure enough, it was a negative slope. And now we can go back and we can check that problem, and we can see this pretty much the same work that we just did with the slope of negative 2. And then when I plug the negative 2 in with the 0.1 and negative 3, I get a tangent line of negative 2x minus 1. And there it is. Perfect negative 2x minus 1. Perfect tangent. The normal looks very perpendicular. Everything's coming together for us. Things are looking up. Number 11, I told you, was the one that I think was going to mess people up. And the way that it's worked out in your course pack, there's nothing wrong with it. It's the kind of the common denominator method. Although it looks like maybe I might have gone through and fixed it at some point, because it looks like I'm doing the cancel the fractions method now, which is kind of the way I have it here. let's definitely work this one out because it's not a polynomial. You still do the same thing, but you still use difference quotient, but the algebra is different, and so because of that, it freaks some people out. So let's take our time here with number 11. Okay, I'm going to definitely write this stuff off to the side because I know that I need to do the limit of f of, what are we using, 2 plus h minus f of 2 all over h, but I don't know what f of 2 plus h is. I don't know what f of 2 is, and so that's what we're going to figure out right now. Doesn't really matter what order you go in. I mean, f of 2 is pretty easy. F of 2 is 1 over 2 minus 1, and 1 over 1 is 1. So, bam, pretty simple, right? That tells you that the point 2, 1 is where we're trying to find the tangent line. F of 2 plus h is a little trickier. You got to remember, I have to put the entire 2 plus h in for that x value, and then simplify. Notice that 2 and then negative 1 makes positive 1. So this is going to be h plus 1, I guess. And so this is what we're going to get once we do our substitutions. F of 2 plus h is 1 over h plus 1, or 1 plus h. And then f of 2 is just 1. Remember, we got that up here, and then it's all over h. So we have fractions within fractions. And like I said, you're welcome to get common denominators. You can multiply by h plus 1 over h plus 1 here and get a common denominator at the top and multiply by the reciprocal at the bottom. That's never how I do these problems anymore. Through experience, I've just found it way quicker to eliminate the complex fractions. So I'm going to multiply by the only denominator, h plus 1. And eliminate any of those fractions. Okay, so here's where you have to really watch your algebra. This is where people get themselves in trouble. When I distribute to the first term, the h plus 1's cancel and I just get a 1. When I distribute to the second term, nothing cancels. And I don't even have to multiply by any special number. It's just going to be h plus 1. On the bottom, I get h times h plus 1, nothing cancels. Don't forget to multiply by the bottom, and you have to show you're multiplying by the bottom, okay? Now, the top is just going to be 1 minus h minus 1. If you forget to distribute the negative sign, the 1's won't go away, and then you will really be stuck, okay? But they do go away, and all I have left is negative h. And that's going to allow me to get rid of that h, which I've been dying to get rid of since the very beginning. This h has been preventing me from using substitution, and now it's gone. And so now all I have is negative 1 over h plus 1. So I can finally do my evaluation slash substitution step. Let's do it. I'm going to get negative 1 over 0 plus 1, which is just negative 1 over 1. Negative 1. There is your tangent slope. Okay. And if we go back and take a look at that work now, maybe it'll make a little bit more sense. This is, like I said, they did the work within the fraction, so it's a little uglier to begin with, but they really did just multiply by the 1 plus h here and so this work is really the same as we just did. Really, so is this. So both of these. I don't know why I redid it over here. Somebody probably did it, asked me about it at some point, and I just like wrote it out in class, and then it was too pretty to get rid of. But once we know that we're ready to take our slope and our point here and plug them into y equals mx pli, I get that tangent equation, negative x plus 3. And then the opposite reciprocal of negative 1 is positive 1. 1's the only number that's its own reciprocal. And so you just take positive 1 with the same point. And look at this picture. So we know what 1 over x is. 1 over x is a graph. It's called a hyperbola, and it uses the axes kind of as its asymptotes. But this one, remember, was shifted over one unit to the right because of the minus one in the denominator. So there is that vertical asymptote. Notice at this point exactly, that's where we're trying to find the tangent. And it does have that negative slope of -1. And look how our negative x plus 3 was perfect with that tangent relationship. Okay, I didn't do any of this graphically. I did it all analytically, algebraically, but when I put it in here, it worked perfectly. And then when I took the opposite reciprocal of -1 and found the normal equation, which was x minus 1, look how perpendicular that is through that same point. Perfect. Very cool to see that in action. I highly recommend once you get your answers, you plug them into your calculators to see how it works. Now there is a little trick you can do to make the perpendicularness look more perpendicular, and that is, well, I'll show you on this last one. How about? So this last one is just another parabola. This time they want it to evaluate it at 0. That actually makes our job a little bit easier. So if I do f of 0 plus h, that's really just f of h, which means I'm just plugging h into my function. So that's going to be h squared minus 3h minus 1. See, much easier. What is f of 0? Well, that's just going to be 0 squared minus 3 times 0 minus 1, which is just -1, right? So we're ready to roll. The limit s, if you really want to label this, which isn't a bad idea, we are finding the tangent slope, so you could call it m. M equals the limit as h goes to 0. Now remember, we're doing f of 0 plus h minus f of 0 over h, but I just found these, so it's just substitution. It's h squared minus 3h minus 1, and then subtract the -1 we found for f of 0, which is in turn going to turn into a +1, isn't it? Because we're subtracting a negative. And so those ones cancel, and I just get h squared minus 3h. I'll go ahead and factor the h out so we can get that cancellation. The limit as h approaches 0 of h minus 3 is just going to become 0 minus 3. Holy cow, every one of these problems had a negative slope, didn't it? Interesting. Once we know the slope is negative, and the point was 0, -1, right? Notice that 0, -1 is the y-intercept because it's on the y-axis. The x value is 0. So I already have my equation. I don't have to solve for it. It's going to be y equals -3x minus 1. That only works. That only works because we're on the y-intercept. Don't think you could always just take the y value and make it your intercept. This one does work. So -3x minus 1 is the tangent slope. The original function x squared minus 3x minus 1, I just got to remember that, and we will plug it in to our formula. It's kind of interesting, isn't it? If I took the x squared away, -3x minus 1 that's left over there is my tangent line. That's bizarre. All right. So that's really what we're trying to do. Turns out I was just trying to add a page. Can I add a page? Yes, I can. All right. So we're going to do x squared minus 3x minus 1 parabola, and then our tangent slope at 0, so it's going to be right here, right, was -3x minus 1. And tangent, look at that, isn't that cool? Now the the normal line would be using the opposite reciprocal of -3, but it would still be using the point 0, -1, so it would still have the same intercept, right? So that would just be the perpendicular or normal line would be y equals positive 1/3 x, but still going through the same point of tangency. So let's do 1/3 x minus 1, and see what we get. Okay, you know what? That actually looks pretty good. It does look fairly perpendicular. Sometimes these don't. Sometimes because of the slopes and stuff, they actually don't look very good. So this is what I was going to show you. You can go into your zoom, and if you zoom square, which isn't in this original menu, you have to go down to the bottom. So it's option B. Zoom square sets everything up so that your your perpendicular relationships look really sharp. They really are. Also, if you ever graph like a parabola, or I'm sorry, an ellipse, and it doesn't look, as elongated as it should, you can use the same option. Or let's say you graph a circle and it looks elliptical, but you know it's a perfect circle. Use this option, this zoom square, and it'll set the values for you so that everything looks very nice. Okay, so cool. Hopefully you only watched this if you really needed to, or only watched the ones you needed. Like maybe some of you guys just needed 11, and so you watched that one, and that was all. Um, 13 and 14 were kind of interesting. Um, they were just playing around with absolute value functions. Don't worry too much about them. It's not a huge focus of what we're doing. But with an absolute value, you just kind of remember that they have slopes of -1 on one half and +1 on the other half. So you have two different slopes for these lines. And so if we're at 2, which is over here, we're definitely going to have a tangent slope that's the same as the line. Linear functions have tangent slopes that are the same as the slope of the line at all points. That's just the way that works out. Now, on the other hand, if we go to -3 back here, where the slope is -1 coming in, if you do the math, look what you get. You get a slope of -1. So depending on which side of that vertex you're on, that's what it's going to be. Now, when we got up to like problem 16, was it 15 through 18 or something like that, and we were testing for tangency, if you do have a absolute value function, you get into trouble if you try to find the tangent slopes right at that vertex, because of the abrupt change in direction, and the tangent slopes don't agree. Now, that wasn't what this problem was about, but I mean, the only tricky thing about this problem really was realizing that if you were at -3, your function wasn't just y equals x. You had to pretend it was -x, because that was the slope of the line there. You had to kind of pretend it was a piecewise function. This one had just been shifted 2 units to the right. And so from 2 backwards, we just pretend it's y equals -x. And from 2 forwards, we pretend it's y equals, x. I guess technically x. Um, the intercept would have been, what, -2 down here. So x minus 2, whereas this one, the yellow one, would have been -x plus 2. Right? So you had to use 2 different graphs and then find the slopes. But like I said, I don't want you guys to put too much emphasis on these problems, because we don't get into that too much. It was just more experimenting around with the idea of direction of slopes. Okay. Now, 15, 16 were kind of interesting. 15 I did for you, actually. I didn't show you a graph, but I just did this work, and I showed you that even though we did have continuity, at the breakpoint, so we were continuous here because we had the same height of 2, that the slope of the left function was -2, whereas the slope of the right function was +2. And so that means that there's no tangent that exists at that point. Um, and this is just a little picture that I kind of sketched, so it's not perfect, but you can see because the parabola is already turned around and is going down, whereas the linear function is always going up, right? 2x plus 2 is just a line. Those functions, those slopes cannot agree. And I think I did a big picture here for you to show you the actual graphed values. And if you take those values, better do it this way. So if you take this, this function slope, it's obviously up, and this one's negative, they don't agree. So we did the work on this one within the lecture, so we don't need to go over this one again. You can go back and watch it in the lecture. But I will work out 16 for you. Okay, I will work out 16. So let's do the right limit and the left. Well, let's check continuity first, I guess. Always check continuity first, because if there's no continuity, there's no possible way that you can have a tangent slope. Okay, so what is the left function at 0? Well, it's 0, right? Negative 0 is 0. What is the right function at 0, which is a parabola? Well, it's 0 minus 0. So it's 0. Yeah, so 0, 0 is the point where these guys are going to meet. So continuity checks out. Always check continuity first, though. And if it works, then you have to check the tangent slopes, see if they agree or not. So let's do that now. So the left tangent is going to be the limit as h is moving, um, h is decreasing, the value of h is decreasing from the left. That's what this means here. Notice it's not x is approaching 0, it's h is approaching 0. But what that means is, if I have a point at, 0, and I have my function, and I'm moving the points closer together, right? So those secants become the tangent. I'm moving the point together from the left, as opposed to how we built the formula the other day from the right. That's what that means. And so to us, it means we have to use this left function if we're moving the point from the left. And so the limit is going to be negative 0 plus h is just going to be h, right? And then if I plug 0 in, I just get a 0. So minus 0 over h. Well, that 0 goes away. So I'm really just taking the limit of negative h over h, which I think we can both agree is just negative 1. So that's your left tangent slope. Now let's switch to the right tangent slope, which is a little trickier because we already knew that the slope of this line was negative 1. So we knew that the tangent anywhere on a line is going to be the same as the slope of the line, which was negative 1. But now we're going to do the right function's limit as the secant's approach to tangent. So we're coming from the right, and the function's x squared minus x. So that would be h plus 0, which is just h squared, minus h plus 0, which is just h. And then if I plug 0 in there, remember I get a 0. So that 0 just kind of goes away. And I can factor an h out. It cancels. And then I am taking really just the limit as h goes to 0 of h minus 1, which is 0 minus 1, which is negative 1. Well, look at that, negative 1 and negative 1. See, in this case, those tangent slopes agree. So the tangent, even though it's two totally different functions here, the tangent will exist at x equals 0. And here is a good way of looking at that. Here's the graph. So here's that line coming in from the left. Here's that parabola coming down from the right. This is the negative 1 slope of the line coming down from the left. Okay, let's tweak it just a little bit. But here is the deal with the tangent. Now notice that, at some point, these are all positive slopes coming down. But remember, as we get closer and closer down here, they start slowing down and turning. And at the vertex, we're going to get that horizontal tangent. Whoa, don't move, dude. okay? And then it's going to start tweaking back up as we wrap around that vertex. And I'm only 1/2 unit maybe away from that vertex by the time I get here, but it is exactly -1 when I get to that point at the origin right there. The slopes really do agree. It looks smooth. That's how you can tell the tangents will, you know, will exist visually, is because it's continuous and it's smooth. And so that was 16, and that was the last problem. Hopefully that makes sense. Here's the work for that. Exactly what I just showed pretty much, but we can see the tangent slopes agreeing. But remember, always check for continuity first. It's the easier thing to check. Yeah, a couple review sessions tomorrow, 8 o'clock, and then again at our normal 3 o'clock. So if this stuff is causing you some questions, please come and see us. Bye-bye.